What's that?
The mic levels look really high, but they don't look high
No?
there. It's too high.
What's that?
The levels are really high.
Huh.
So maybe you can turn the source volume down.
Sure.
You could be able to, let's try testing
1, 2, 1, 2. Is that okay?
still on the high side. Maybe one down.
Hello? Ready?
That's about right. Don't scream.
All right, good afternoon. That was kind of tepid. I know it's really cold outside. Good afternoon. Good afternoon. There we go. All right. I won't talk a lot about Big Ten basketball. The Badgers took a little bit of a beating on Saturday. Michigan's number 2, though. That's a good sign. Big game with Sparty tonight for Wisconsin. All right, a couple of announcements before we get started. The most important one for you is probably around your homework assignments. Because of the way the lectures are sequenced, this homework assignment does have a problem that includes today's lecture. So we have pushed the due date for the homework to Friday instead of Thursday. That gives you an extra day and gives you some extra opportunity to talk to the GSI if you have any questions. Vineet did send out a digest that's got information on office hours, locations, and times, so make sure you take advantage of that. And he'll typically start the office hour with running through some discussion problems and some sample calculations, and then he'll open it up to questions. So make sure you use that time. It's there for you. All right, what event happened yesterday? Important in U.S. history. Inauguration. I mean, it's been 150 years since the Emancipation Proclamation. It's been 50 years since the March on Washington. So yesterday's inauguration was very important historically. But there's something I think that's incredibly important tied into this course. And President Obama said, quote, "We will respond to the threat of climate change, knowing that the failure to do so would betray our children and future generations." This was a key point of his inaugural address. I mean, this, of course, talking about future generations has got sustainability written all over it. I mean, that's our definition. And so climate change will be a huge focus of his next 4 years in office, and something he's probably going to have to jump on pretty quickly. Any thoughts on what he can do to reduce carbon emissions? Go ahead.
High-speed rail development.
High-speed rail. I think that's an opportunity, one that's probably pretty pricey, but that hasn't been talked about a whole lot. But that's, you know, anything to reduce getting people off the road would be important. He's already increased fuel economy standards going out into the future. What else? Remember in our discussion we talked about some of the largest sources of carbon emissions. Go ahead. Yep, well, he tried cap and trade, you know, in 2010. And unfortunately, Congress didn't pass that legislation. But he's going to have to look at some sort of tighter restrictions on emissions from power plants. Now, he may do that through executive order rather than waiting around for Congress to try to figure it out. But that's certainly, I think, when we look at the total emissions for the country, hitting power plants will be a big one, and one that I'm sure he'll wind up going to court about. The other thing that's been discussed is just improving on energy efficiency of household appliances and household equipment. It's something that seems like kind of a drop in the bucket, but anything to reduce our overall electricity usage will reduce our carbon emissions. So again, yesterday was a historic day for a lot of reasons, but I think as an engineer and somebody who's interested in sustainability, you might keep January 21st as a date that things will start to happen with respect to climate change. Okay, what I'm going to start with is just a brief recap of some of the items from our last lecture. I just want to make sure we're all on the same page regarding some of the topics. First, regarding our summary on reserves and the resource base. You may recall we talked about the resource base being this box that essentially is fixed, that captures all of the resources that are available for extraction. Reserves are the amount that a subset of the resource base that will be extracted, and that this bar will move in terms of the total discovered resources based on our prospecting activities. The amount of mineral, for example, that's extracted, again, will change depending on our technologies that are available. So this large box is fixed. This smaller box can move, just like when you're enlarging or minimizing an image on your computer. You know, this rectangle can get bigger or smaller depending on economic, political, and technical factors. We did talk about some consumption models, the exponential and Gaussian models. And the Gaussian model, or the exponential model, is one that we can describe fairly simply mathematically. We can integrate this function and identify our production rate in terms of the starting production rate and a log function. Now, the total production will be the area under this curve, and again, we can take an integral and come up with a fairly simple mathematical description of the total production. One analogy to this exponential growth rate is the growth of bacteria. They double every 17 minutes, and if you were to plot the growth of bacteria over time, it would be the same sort of function. The Gaussian consumption model is one that's probably a bit more accurate and one that's a bit more realistic. But the ideal Gaussian model, again, has a somewhat uniform production curve. We're really interested in how big this curve is and where this maximum time for maximum production is located. So we can, again, come up with a mathematical description of this production curve. We can estimate the ultimate production, the area under that curve, and we can characterize that ultimate production in terms of this peak production number and the standard deviation, one standard deviation, basically the size of the area under that curve. We used oil production as our model for discussing Gaussian production. That discovery curve can follow this dotted line. Our production curve looks like this, and that dotted line is, again, speculation. Oil production and predicting when we will hit this maximum production rate is one that's been bantered about. I think there were some that mentioned, well, we hit that peak production in 2006, 2007. Others say, well, we're not going to hit that out until 2020. So again, it's open to a lot of speculation. But the driver for that, again, that can stretch out that time frame is improvement in technology. Go ahead.
Have we seen any models, any resources go through enough of the life cycle that we've seen this Gaussian consumption model sort of verify? I mean, I understand conceptually it makes sense, but have we seen anything sort of verify it?
I've got to think about that one. I know that in lecture we did have some examples of exponential growth models for some metals that seem to follow that model pretty well. I think oil is an example that probably is fairly representative. Natural gas, I think you can kind of throw out the window now because through processes like fracking, we're opening up much larger reserves of natural gas than we thought we had. So And we haven't run out of anything yet, really. So I don't think we've seen that final curve, but that's why this is speculative. Of course, oil is a critical material that we're using. So, we haven't seen that dip yet. We don't really know where it is. Again, through fracking and other technological improvements, we probably haven't seen that peak yet. And I've got a slide here that's going to talk a bit more about oil specifically. I want to briefly summarize one of the problems that we solved, and we looked at production of U.S. coal, and we estimated that the ultimate production was going to be 2 times the estimated reserves, which was, I guess, an assumption as any. We had our 1995 production rate, and what we wanted to know was how long is it going to take us to hit this peak production rate, which we assumed would be 4 times the current rate. And so, again, we have an expression to solve to get this peak time, and it's all going to be dependent on the standard deviation along with those estimated rates. So we took our ultimate reserve and we rearranged terms to solve for sigma, our standard deviation. We plugged in our assumed numbers and we got a standard deviation of 53.5 years. And when we plugged sigma back into this formula, we estimated that peak production time to be 89 years. So again, these results are all going to be dependent on some critical assumptions. You've estimated a reserve. Well, we're going to assume it's going to be 2 times the reserve. We have a given production rate. Let's assume that we hit our peak at about 4 times that rate, and then we can calculate what that time is. So we can come up with kind of times to extinction, and it's all going to be dependent on sigma, really, and how big that curve is. So back to your question, are we running out of mineral and energy reserves? So here are some slides. I'll focus here on our natural gas production and our crude oil production in the U.S., and you can see that this natural gas production curve is now on a big uptick. And again, it's really driven by all of the unconventional shale exploration that's done in Pennsylvania, Ohio, North Dakota, and elsewhere in the U.S. Now, our oil reserves, that estimate has been decreasing, but that's seeing a bit of an uptick now as well. And we do have a fairly large unexplored area in the Arctic, and that exploration of that area is quite controversial for a number of reasons. The economics, of course. I think recently you may have heard that Shell was setting up a large exploration platform in the Arctic. They had to get it done within a certain time frame. They had technical difficulties. Well, they basically missed the season in which they could establish this platform, so they're pushed off into next year. So these things happen. These things cost a lot of money. But technical innovations, again, we talked about fracking and pulling out reserves in the continental U.S. that we just weren't aware of before. So are we going to run out? I don't know, but certainly, we didn't run out of stones to end the Stone Age. So I think, through these technological advances, we're opening up more reserves, more energy reserves than we thought we had, but they are finite. They're not renewable. So why do we care about resource consumption? We're coming up with these somewhat theoretical models. Well, one big reason is that the energy intensity, in other words, the amount of energy that we have to input to extract a given amount of resources, is likely to increase. New reserves, as I mentioned, the Arctic could be located in fragile ecosystems. And again, there are going to be other social and political issues to explore those reserves. And finally, the ecological impacts. Was it that bad? Did she sign in the sheet? That's the key question. Okay, I'm back. Okay, I think I'm okay now. Okay. All right. That's a summary of what we covered in last week, and so now we're going to move into recycling. And I think I mentioned to you when we first introduced the course that my mother-in-law has got to be the world's best recycler. She lives sustainably without thinking about it. How many of you, when you're done with a jar of jelly, rinse it out and drink it because you don't want to waste it? Okay? This is the level of recycling this woman has incorporated in her life. Now, as an engineer, it's in your DNA to optimize systems and look at recycling. Sustainability in that sense is nothing new for engineers. We've always looked at reducing energy and reducing resource consumption and optimizing systems. So what we're going to talk about today are some mass balances and how to incorporate recycling into understanding material flows. So I've got a couple slides here regarding recycling. I think, all of you have seen these sorts of tags on the plastics that you use, and reusing PET containers and other plastic containers, I think for now is a pretty standard way for us to manage wastes. One example that I wanted to talk about was battery recycling. Lead-acid batteries are used primarily for transportation and manufacturing plants. But that battery can be recycled in a number of different ways. The plastics can be reused. The lead in the battery can be used as a source material. The electrolytes can be recycled in a couple of different ways. So lead-acid batteries are a pretty good example of recyclable materials. Now the print here is pretty tiny, but again, I just want to emphasize that whether it's metals, plastics, ceramics, all those materials now can be recycled, and it really comes down to an economic question more than anything. Okay. Yeah, I'll just stand right here. Sorry about that. Okay. All right, I can't sing and dance in front of you, so I'll be much more professional. I think it's interesting to note that graphic on the far right side does demonstrate some recycling metrics by nation. And in the U.S., we recycle probably between a quarter and a third of our wastes. In the federal government, as part of President Obama's executive orders, they're typically shooting for 50% recycling at federal facilities. So we've got a ways to go, but that's a fairly common recycling number. If you look at countries like Germany, a little more environmentally aware, the value of recyclables is higher, and so their recycling rates are representatively better. When it comes to, let's just look at the U.S., over time, this is 1990 compared to 2003, the amount of paper recycling that we do is pretty high. Glass is still fairly similar, hasn't changed a whole lot. People in Michigan often complain about the 10-cent returnable laws, but we certainly don't see cans and bottles on the sidewalk in our roadways or in the cafeterias. So there are a lot of benefits to adding a little financial incentive to our recycling. Okay, so as I mentioned, as engineers, we like to optimize processes, and one way that we measure how our processes are working are at using material balance and material mass balance calculations. So one critical assumption in doing these calculations is that we're essentially at steady state. So the mass coming in will equal the mass coming out. We're not accounting for any system losses. We're not accounting for any material losses. We don't have any defective materials. You know, of course, it's a very basic assumption that we don't have, that we really have a steady state scenario. But you know, when we take this to another level, we have to account for all those potential losses in the system. So if we look at our production process and simply call it a black box, or in this case a beige box, we're going to assume that essentially the mass going into the process is going to be the mass going out. So again, that's a very important assumption when we start putting together some equations on mass flows. Now in recycle systems, we're going to add another loop to all of this. And so one factor that we have to think of is time. And so we will look at the life, sort of the expected use time of a product, or we're going to call that delta T. When we're considering the production process as a black box, you know, delta T will be the same going in and out. And so our mass going in and out will still be the same. But we are going to incorporate a time factor because a product is going to have a certain lifetime before it's recycled, and we have to incorporate that time into our calculations. Okay, so when we look at production of a given product, we're going to be characterizing box after box within the process. And so our challenge here is to track that mass, M, of the material through its life cycle stages. We're going to come up with a box for production use, one for production, one for the actual consumer use, and one box for disposal. And again, we're going to assume that we don't have any losses along the way. I work for a company that manufactures chocolate milk. And if you've ever seen chocolate milk production at 720 bottles a minute, it's pretty amazing because the bottles just fly. And the bottles, every single bottle is essentially photographed, and it's checked to make sure the level of milk in the bottle is right, the cap is on straight, and this is all done automatically. And if there's a defective bottle, poof, it goes off to the side and it's dealt with. So production is never going to be 100% without losses, even when you're making chocolate milk. So for the purposes of our discussion, we're going to assume that we don't have any losses. So we know the mass going in. We know, for example, at 720 bottles a minute, you know, X number of gallons per day per year that will go into production. So the question is, what is our mass going to be out of production through consumer use and following disposal? And again, in this case, we're going to assume that we don't have any losses, that mass is the same in each one of these steps. Those 50,000 bottles of chocolate milk are going to go into production. They're going to be, same amount's going to be used by the consumer. And in this case, we'll have those empty bottles going to disposal. So the next thing we want to do is take a look at what happens when we add a recycling loop to this system. So the term we're going to introduce here is a recycled fraction, lowercase f. Okay. So lowercase f is that fraction after the consumers use the product that's going to go back into recycling. Maybe chocolate milk bottles aren't the greatest analogy, but let's assume that we're just looking at production of PET bottles, because then we've got a couple different things we can discuss. So those chocolate milk bottles, some of them are going to wind up in the trash, but a fraction of them will be put in blue bins, and they're going to make their way back into a PET recycler. So that recycled fraction F will vary 0.1, 0.2, 0.3. Those will be somewhat optimistic numbers for a typical consumer product. But then that 10, 20, 30% of PET won't go to disposal. It'll go back up into the recycling process and into production. Okay, so let's look at a problem where we have a recycle loop in the system, and we want to calculate essentially what M is going to be going through this process. So again, we take raw PET, we make bottles, we fill them with chocolate milk, we sell them at the gas station, the consumer uses them, and puts a given fraction into the recycle bin. So our production, we're going to use that mass using a subscript M, and M times F, that fraction will be going back into the recycling process. So for example, if we had 100 bottles and our F is 10%, it's going to be 0.1 times 10 going back into recycling. So again, we're assuming no losses in recycling. Everything that goes into the recycling process is coming back out of recycling. And so if you were to sum M times F with M times 1 minus F, you'll get M. And we have a relationship for the amount of raw material going into the system, the amount of material going into recycling, and all in terms of M, our mass that's coming out of production. Again, pretty simple recycle loop and a way to characterize the mass coming out based on the recycle fraction. Any questions on how we put together that arithmetic? Okay. So we assume that we don't have any losses in the system, so our mass going in is going to be our mass going out. So our virgin material going in here was M times 1 minus F, and that will be the same mass going out into disposal out of the process. So again, with an internal closed loop recycle, we can characterize the mass going into recycling as M times F, the raw material coming in, and the waste going out is going to be M times 1 minus F. All right, so now let's incorporate losses into the system. So we've set up the similar sorts of loops as we did before. We've got production, use, a fraction going off to recycling. But now, when we take those PET plastic bottles, all the material, some of it's not suitable for recycling. We lose some material in the recycle process. And so we're going to introduce a new variable called capital F, which is going to be the fraction disposed. So as before, we had our raw material M as one of our primary variables. M times F is the fraction that's going to go off to recycling. Of the fraction that's going to recycling, we have some fraction that's going to be disposed, so that will be M times lowercase f times uppercase F. From our previous mass balance, we know that the mass that's going to disposal after consumer use is going to be the total less what is recycled. And if we add this mass fraction and combine terms, then the raw material equivalent going out to disposal is M times 1 minus F plus the fraction that's disposed. So again, if you do the arithmetic, what's going into recycling is M times F. We lose the fraction to disposal, and then the fraction that's going to go back into production will be 1 minus capital F. And so to complete our mass balance, again, no accumulation or loss within this loop, so the mass going into production will be the mass ultimately going disposed, and again, we do have this internal recycle loop. So it's all straight arithmetic. If you're not sure how we arrived at some of these subsystem masses, just start adding them up. So you know that, for example, what is m times lowercase f going in has to equal what's going out. So again, you can do the arithmetic. Those are going to equal. What's going into production here is going to equal what's going out at the end. So if you need any work in convincing yourself of this stuff, just do the arithmetic and you'll see how the fractions fall out. Okay. Now there's an important impact on all of these calculations based on the lifetime of the product. A product with a shorter lifetime that's recycled will be able to pull more of that product into the production process. If you have a product that has a lifetime of 30 years, it won't be the mass won't be recycled as frequently, and so it'll have a lower relative contribution to the production of that material. So again, material that's dispersed as a product isn't going to be a scrap until the product really comes to its end of life. So if we look at the logarithmic production rate, an important parameter, our delta t, is going to be the time that the time period that the product was in use, or the time that it was disposed less the time that it was produced. So now we're going to incorporate a temporal factor into our recycling calculations. We're going to introduce a couple of terms. The first is the recovered fraction, capital R. So this will be the amount of that recycled product that's recovered, which is going to be the fraction that goes to recycling times P naught, the initial production rate. So capital R will have units of mass over time. It's simply a fraction times our production rate. The product lifetime, delta T, again, is the time that it was disposed less the time that it was produced. We have, again, from our logarithmic growth model, the production rate is a function of the rate of increase of production times delta T. And this ratio that we're interested in is going to be R over P. So it's the recovered fraction, the amount of that material that's coming out of recycling and going into production, divided by the production rate. So this will be unitless. So the R, for example, will be mass over time, tons per year. And P is going to have similar units of mass over time. So this ratio will give us an idea of what percentage of the recycled material is going into producing that product. So we're going to walk through a couple of problems to illustrate the use of those equations. So we have a problem here where we're assuming that the consumption of the product follows the exponential model, and it's going to grow at a rate of 5% a year. The other assumption going in is that 60% of that material will be available for recycle at the end of its life. So what we want to do in this exercise is take a look at how the variable of lifetime of the product is going to influence the fractional contribution of the raw material supply from its consumption delta T years ago. So we're assuming right now that the consumption rate increases at 5% a year. That's going to be the same. We know that 60% of the material that we use can go back into recycling. And we're going to look at the impact of different product lifetimes on the contribution of the recycled product to the production of the product that we desire. So I gave you an equation before of the recovered fraction versus the production rate. Again, that's going to be unitless, because this will be, for example, tons per year over tons per year. And that's going to be a function of our recycle rate, our growth rate, and the product lifetime. So given from our problem statement, we know that the growth rate is 5%, and we can recycle 60% of the product. So now we're going to set up some calculations. So our delta T here is 1 year, 3 years, 10 years, and 30 years. And so if we plug in to our equation, we know that again, F is 60%, R is 0.05, and delta T here is only a year. So when we have a product lifetime of a year, 50% of that recycled product is going to go into the current supply. If we increase delta T to 3 years, we're just substituting a different number for delta T. Again, the product has a longer time frame, so as you expect, the amount of recycled product going into the supply will be less, and it drops to around 52%. If that product lifetime extends to 10 years, again, there will be less recycled material going into the supply, and that fraction drops to 36%. And if we look at a product that will last 30 years, do we have any products these days that last 30 years? I don't know. That percentage will drop to 13%. So it's, I think, fairly intuitive that a longer recycle time will lead to less of that, or a longer product lifetime will lead to less recycled material into the supply. I mean, that's all fairly intuitive. We now have a way to actually calculate that percentage. So if we look at a summary graph, and if we plot the numbers that we just calculated, we looked at a recycle fraction. We were looking at a 60% recycle fraction, and we characterized the fractional contribution to the current supply. And we looked at product lifetimes of 1, 3, 10, and 30 years. We know that as we increase the product lifetime, here example from 1 year to 30 years, the amount of recycled product in the supply went from 57% down to 13%. As the recycled fraction goes down, you can follow this line, and clearly if you're recycling less, the amount of the fractional contribution of recycled material going into the product will decrease. Would I base everything on 2 points? Probably not, but again, at least you have a model of what that'll look like. And we didn't calculate different growth rates, but of course, if we're not growing as fast, we won't be using as much material, and it won't wind up in the supply. So there were some assumptions that went into these calculations that are pretty straightforward. The material was only used by only one product. Our recycled fraction remains unchanged with time, and I think that's an overly simple assumption. And again, we assume we didn't have any losses in the system, that the mass going in was the mass going out. Okay, so we've got some fairly simple arithmetic expressions to start to characterize what happens when we start increasing product lifetime and what kind of impact that has on recycling. Okay, we're going to make this a little more complicated now. So now we're going to look at the effect of product lifetimes with multiple products. And I'm going to walk through this problem carefully. We're changing a lot of different variables, but it just gives you an idea that we can start to characterize material flows using these simple systems. So now we have a material that's consumed by 3 different products. And we're assuming that the consumption for those products grows exponentially at 3 different rates. And again, we typically would like to change one variable at a time, but the purpose of this problem is just to show you that we can handle multiple variables within these calculations. So we've got recycling rates for the products that vary, 40 to 70 to 30%, and we also have varying lifetimes of these products, 10 years, less than a year, and 30 years. So again, we've got multiple scenarios for this given product. Now, we are going into this calculation, we're assuming that the products account for 50%, 30, and 20% of the material consumption. So again, we've got all of that material spoken for in these 3 products. So what we want to do is calculate really the contribution to the supply from each of these products. So we have a given mass of a material, and we want to understand what kind of contribution into the supply of the products the 3 different recycled products have. So we have an equation that's simply a variation of what I gave you before on R over P. Again, this is going to be unitless. It's going to be tons per year over tons per year, for example. But what we've added is this S sub I, which is going to be a fraction of the total material that's consumed by the product. So again, we're assuming that this material is being divided up into 3 products. We don't have any other side streams. We don't have any other wastes. So if we set this up for the first product, our growth rate for this first product was 6%. The fraction that's recycled is 40%. Our product lifetime is 10 years. And we know that 50% of our material is going into this product. For product 2, again, out of the problem statement, growth rate of 4%, 70% recycling, very short product lifetime, but 30% of the material goes into that product. And for our final product, it's got a much slower growth rate, a lower recycling rate, a very long product lifetime, and it's taking about 20% of the material going in. So you can set up these calculations pretty easily on a spreadsheet, just varying the various variables that go into this. So if we look at our first calculation, we're looking again at the contribution to the current supply from recycling of this first product. And so we plug in the fraction of that product, SI, which is 50%. We know that 40% of it's recycled. We handle our growth here through the logarithmic function of the growth rate times the product lifetime. And we calculate that just a little over 10% of the recycling of product 1 winds up in the current supply. For product 2, we dump in those different variables, and again, it's recycled at a little higher rate. The growth rate isn't the same, but it's got a very short product lifetime. At the end of the day, it's about 21%. And so for product 3, we pop in those variables. Again, it's got a much slower growth rate, a very long product lifetime, and as expected, it's going to have a much lower contribution into the total supply. So again, go ahead.
Maybe you were going to address this, but when is it significant to understand these values? Why, on any given year, we know that there's going to be these initial recycling rates involved, but to estimate from a certain product year how much is still in the stream, the value of that.
Sure. Well, let's say that you were the manufacturer of this material, and you've got to predict how much of this stuff am I going to produce, how much of this am I going to sell. So if I'm a plastics manufacturer, and I know all the plastic I'm going to make is going to go into these 3 products, I know what some predicted usage rates may be down the road. I know that my customers are going to produce so many bottles of chocolate milk. How much plastic am I going to sell them? Well, if you don't take into account the recycling rates, you're predicting that you're going to produce a heck of a lot more material, and you won't be able to sell it, for example. So you want to have an idea of how much material you actually need. If I'm on the customer side, I need to predict, for budgeting purposes, I need to predict how much plastic I'm going to buy, for example. Well, I don't really know what my recycle usage is. If I don't know that, I may buy too much raw material going in. So, these are, again, fairly simplified models because we're assuming steady state and we don't have any losses. But these models have some very practical applications for people that are buying and selling raw materials and trying to predict how much they're going to use. Go ahead.
So are we assuming that the recycled material goes back to the producer? Or just back into the general stream?
Well, we haven't couched who's making what. I mean, this could be a single, for example, a single producer of a material, of a product, for example. And what we're trying to predict, he's trying to predict, for example, let's say if he does his own recycling, then he needs to predict how much material he's going to need to buy. But, I mean, you could throw a whole variety of scenarios here in terms of who's the producer and who's the recycler and how much you're going to use. Now, it's all a matter of scale. If I'm a guy in a plant, the scale is pretty small. If I am somebody who's perhaps buying futures in plastics manufacturing, well, I want to look at this thing maybe on a national scale. How much plastic, how much PET is being used by all these companies, and how much is getting recycled, and kind of what can I expect in terms of the market for raw PET. So, again, a lot of this depends on scale. You can look at this at a very small scale. We're doing this fairly simply in terms of a couple of products, or you can be looking at a whole market for PET and what's the expected production of PET for the country. Okay? Okay, one concept that doesn't get talked about a whole lot is downcycling. In downcycling, we're essentially taking recycled materials and producing a product that may not be as of high a quality as the original product that we started with. So we're going to look at one example here. And we're going to take this same example, but we're going to assume this time that we're going to take 20% of the recycled material from product 1 and 40% of the recycled from product 2, and we're going to make product 3 out of it. We really didn't discuss the quality of these products. I think it'd be fair to assume that in a lot of cases, recycled materials don't have the same product characteristics and product quality as the original material. But in this case, we're going to, again, do some calculations to see whether are we going to need any virgin materials at all to produce product 3? So here's a pretty good example. If I'm a producer of product 3 and I can get my hands on some of these recycled waste streams, they might be cheaper. Am I even going to have to buy any raw material going into this? So we set up the calculations. These are the same calculations that we had before, where we basically ground out the recycled fraction for these different products. We had, again, 50% of that raw material, 30%, and 20%. So now, for product 3, it's going to be using the recycled fractions from product 1, product 2, and its own product. So we know that what we're doing now is we're substituting, our recycled percentage is now 20% from product 1, and it's 40% from product 2, and we have our original product 3 recycling. So the amount of recycled product that's going into product 3 went from 4% up to 22%. And the question is, are we going to need any virgin product at all? And we basically took 20% of the virgin material. We're getting actually 21% out of recycling. So we may be able to get by without any raw material at all. Okay, now recycle percentages typically won't be constant, and so you may be looking at a function of recycling that's going to be kind of a step function because it's going to change with time, and this is just a simple mathematical model. But the production growth rate here is of the raw material is going to be changing based on the recycle function. So here, if you're recycling 90% of the material, you're not going to be using much raw material in your process. Over time, if you're not recycling any, then of course you're following the standard growth model. So the recycling rate will have, of course, a huge influence in determining this production rate, and it's going to change over time. Now, if we've talked about constant recycling rates, and this will lead to a nice smooth function. But again, it's likely that recycle rates will change over time, and so you can see some dips in that curve. With the curve's going to change, the production rate's going to change based on whatever the recycle rate changes to at that time. Okay, so to summarize our lecture today, we reviewed product reserves versus the resource base. Remember that the resource base is a fixed box, and the reserves are variable depending on technology and regulations and economics. We have a number of different production or consumption models. The exponential model is pretty straightforward. We use that in some of our mass balance calculations. The Gaussian model is a little more realistic. But you've got the tools now to calculate some peak production. Okay, just settle. Nobody has to start moving their stuff around. Okay, we're in no rush. We can use the Gaussian model, a little more realistic model. But again, all these models are going to be very sensitive to those input parameters. So those curves will be broad or narrow depending on some of our assumed peak production rates and times to achieve those. We talked about closed-loop recycling. You now have equations that you can use to calculate masses in and out in a mass balance equation. My advice is just draw it all out, and you can do the arithmetic to add up masses coming in and out of your unit boxes. We looked at the impact of product lifetime on recycling with both single and multiple products. A product with an extended lifetime, of course, will have less recycled material going back into the product supply. And we talked about using recovered materials from one product and dumping that into another product. And you can simply add those recycled fractions going into a product to determine whether you need any virgin material or not. Okay, so go ahead. We used 20% of the virgin material going into that product, and basically our recycled materials made up for that virgin material mass that went in. Okay, a couple of important notes. Make sure you go visit Vineet if you've got questions about doing these homework problems. Like I said, he's going to start with a discussion problem and then answer some individual questions. You've seen that probably our reading assignments to date haven't been particularly long. This recycling one was really pretty short, pretty straightforward. Our next lecture on Thursday is going to cover a lot of global environmental issues, and the reading is pretty dense. You don't have to memorize it by any means, but you should be certainly familiar with the concepts that are in there. You don't have to memorize regulations, but understand the various media and what the most important issues are, whether it's water, air, land, and associated impacts. So I think that's about it. Any questions, administrative or material-wise? Go ahead. Hold on. Where is the sign-in sheet? I think it's still making its way around. Okay, it's right up there. Okay, thanks. See you on Thursday.